So today we're going to look at kind of a special case when we're looking at moments, and that's this thing called a couple. Now, a couple is this pair of forces that are parallel. They have the exact same magnitude, but they act in opposite directions, right? So the sum of these forces would actually be zero, but they do create a moment, right? There is kind of this desire to rotate created by these two parallel forces acting in opposite directions. This is a special case that we see, but it is something that we see all the time in real life, right? So you can think of when you're driving your car and you want to turn your steering wheel, you'll apply a force where one of your hands is going up and the other hand is going down in order to rotate the wheel. So that's kind of this idea that the one force pulling up, one force pulling down, they're the same magnitude, and there is a perpendicular distance d between those two forces that is causing this desire to rotate, this moment. We occasionally will call this moment of a couple, this is a free vector. A free vector. Meaning that it has the same value if you apply this at any point. So if you were to take this pair and apply it at any point, the moment would still be f times d. It doesn't matter where you're taking the moment. The moment will always be f times d for a moment couple. So if we look at like a super basic example of what that means, let's just say we have some beam here. And we'll say we have some beam here. And I've got 100-pound force acting upwards at point A. And then let's say a foot later, I have 100-pound force acting downwards on my beam. Right, and we'll call this point B. And we'll call this point C down here. Let's say point C, who knows? Let's say it's, I don't know, 10,000 feet away. Point C is 10,000 feet away. The idea with a moment couple and the idea with a free vector is that you can take the moment about any point along this beam, and the moment couple is going to give you the exact same result. It's still the moment going to be the exact same no matter what point you take it about. So in this case, if we take it about point A, the moment about A is going to be this force. This force is not going to matter because it goes through our force line of action goes through point A. So all we're going to have is this 1 foot times B and then 100 pounds, right? And that's going clockwise. Right? 100 pounds, 100 pound feet, 100 pound feet clockwise. Right? 1 foot times that 100 feet down. Same as if we took the moment about point B, right? Took the moment about our point B here. Now we wouldn't count this force, right? The line of action of this force is going through point B, so all we care about is this 100-pound force up here. So that's also going to be 100 times 1 foot. 100 times 1 foot gives me 100 pound feet. And again, it's going clockwise, right? So these are the exact same, even though we took the moment about two different points. And if that's not convincing enough, we could take the moment about point C over here, right? And we could say the moment about C is going to be my 10,000 feet, right? 10,000 feet times 100. And that's going in the counterclockwise direction. Right, so I'll make that a positive. Minus, right, because this one is going in the clockwise direction, minus 10,001 feet. 10,001 feet times 100. So I still get the same answer, right? 100 pound-feet clockwise. It doesn't matter where. I could take it anywhere on this beam and I'm still going to get the same moment. That's the concept with the moment of a couple. A couple is always going to give you that F times D. That is the moment of a couple. Let's take a look at some actual examples. In this example, we're given a little triangular piece of sheet metal, each with side lengths of 4 feet. And then there are 3 couple forces acting on the triangle, right? So you have 150 pound, 200 pound, and 300 pound forces acting on this little triangle, and it wants us to find the resultant moment. So all we'll need to do for this is take our moment is force times distance for each of the couples and sum those together, right? So we'll need to determine direction for each of them, and then we'll just be adding them together. So if I look at my 150 pound one, my direction of rotation just follows the arrows, right? So it goes in this motion, right? In a counterclockwise motion. If I'm just following the circles that the arrows make. So here I have my moment. Counterclockwise is positive. We usually assume counterclockwise is positive. My moment will be 150 times the 4-foot distance between the two forces, right? So my 150 times 4. Then I'll move on to my next couple. I have a 200 pound force going out and going in towards the triangle. Again, making this counterclockwise circle. Right, so plus 200 times 4. And then finally, my last pair down here, I have a 300 pound force and a 300 pound force, which again is going counterclockwise. So plus 300, and the distance between those is also 4. So what I end up with is my resultant moment. My resultant moment is just 2,600 pound-feet. And notice again, we weren't taking the moments about any point in particular, because for this definition for couples, it's just force times the perpendicular distance between those two forces that make the couple. Let's look at another example. Now this example asks us to find the force F, and it gives us the resultant moment, right? It says the resultant moment is 1.5 kilonewton meters clockwise, right? 1.5 kilonewton meters clockwise. That's what our resultant moment is. I'm going to go ahead and write negative 1.5 is our resultant moment. And we can see in our diagram here, we have this beam with two different couple moments listed on it. So the one in green is one that is known, right? We have a known force and a known distance between them. So this pair here is going counterclockwise. So we have negative 1.5 equals 2 times 0.3. And then we'll put in our F couple moment. If we draw the circle around that, we'll find that one's actually going clockwise. So that will be minus F times the distance between them, 0.9. So now all that's left to do is solve for F, right? So it was just summing those two couples and setting that equal to the resultant moment. Right, so I have 1.5 equals 0.6 minus 0.9 F. If I add this 0.6 over, I have negative 2.1 equals negative 0.9 F. So my force vector, the magnitude of that force vector for F and negative F is going to be 2.33 kilonewtons. 2.33 kilonewtons. So we can use it to find the forces, find the distances between those forces, or find resultant moments. Let's do one more example where we do look at finding the distance between the two vectors. In this last example, now we're working in a 3D space, and we have our moment couple in this 3D space where we know it's a moment couple because we can see that all of the I hat, J hat, and K hat terms for our forces are the same magnitudes as each other, but each flipped in sign, right? So F has a positive 8 I hat, while negative F has the negative 8 I hat, right? So what we want to do is we want to find the distance between these forces, and how we're going to do that is by taking a moment and then backtracking that moment using F times D. So we're going to take a vector form of the moment, make that a little bigger. Moment is R cross F, and converting that into a couple moment using the FD formula. So let's talk about what we mean by that, right? So our moment, R cross F, what I'm going to do is take a moment about point A here, this point right here. I'm going to take a moment about point A, and I'm going to create an R vector from A to B. A to B, this is our R vector. And I'm going to take the moment of this R vector crossed with our F vector here. Right, so this is going to be the moment is our R vector. Whoops, sorry, that's an I, J, K, R vector, and then the F vector. So that F vector on the bottom is 8, negative 4, 10. But we'll need an R vector, which we can get pretty simply, right? Because we're given these distances listed already on the grid for us, right? So going from A to B, our R vector, the X distance here is 4 meters plus 2 meters. So it is going, oh, that's the Y direction. So the Y component, it's going in the positive Y direction by 6. Our X components, 3 meters and 3 meters, so it's going backwards in the negative X direction, right? Negative X direction by 6, negative 6 I hat plus 6 J hat. And then it's going from point A to point B, so it's from 5 meters in the Z direction down to 0, because B is in the XY plane. So that's going to be 5. 6, 6, 5 are the components of our position vector. So now we can do the cross product, right? All we did was find our position vector. We can get a moment from this. So our moment is going to be I hat times 6 times 10 minus 5 times 4. Oh, this is a negative 5, isn't it? Our Z component is a negative 5. It's going from a positive to a negative. It's losing it. Negative 5. Negative 5 times negative 4. My mistake. All right, minus J hat, which is negative 6 times 10 minus 8 times negative 5, plus our K hat, which is negative 6 times negative 4 minus 6 times 8. If I add all those together, what I'm going to get is our moment is 40 I hat plus 20 J hat minus 24 K hat. So this is the moment, right? And we can use this moment, find the magnitude of this moment, right? This is it in vector form. We can find the magnitude of the moment and divide by the magnitude of the force to get d, right? From our moment equals F times d formula. Let me move this stuff out of the way. And let's do the math here, right? So our moment is F times d. So we can find the distance between them by saying d is the moment divided by F. So all I need is the magnitude of the moment and the magnitude of the force, right? So magnitude of the moment, just square root of the squares. Square root of 40 squared plus 20 squared plus 24 squared. And that gives me 50.57 Newton meters. And the magnitude of my force, again, square root of the squares, my components were 8 squared plus 4 squared plus 10 squared. If I square root the squares there, I get 13.41 newtons. I can plug those back up here into my formula. D equals 50.75 over 13.41. And that gives me a distance of 3.78 meters. And that's it.